Every time a train passes by, most people notice the same things: the powerful locomotive, the endless wagons, the steel rails cutting through the landscape. But almost no one pays attention to what is actually holding the entire railway system together. The stones, thousands of crushed little rocks placed under every railway track around the world. At first glance, they look simple, almost insignificant. Something that could easily be replaced by soil, sand, or concrete. But in reality, those stones are one of the most important engineering discoveries in the history of railways. Without them, trains would sink into the ground, rails would lose alignment, and railway systems would become unstable and dangerous. What makes this even more interesting is that railways were not always built this way. In the early days of the railway industry, engineers placed tracks directly on soil, stone blocks, and wooden foundations, and the results were far from safe. Over decades, railway engineers had to solve one of the biggest challenges in transportation engineering. How do you support thousands of tons of moving steel on unstable ground? From the first steam locomotives in the early 1800s to modern high-speed rail systems, the solution slowly evolved into the ballast system we see today. So why do train tracks have stones? Who invented this system? And what happens if those stones are removed? In this video, we are going to explore the engineering and history behind railway ballast, from the birth of railways in the 19th century to the modern infrastructure that keeps trains running safely across the world. The story begins in 1804. That was the year British engineer Richard Trevithick built the first steam locomotive capable of running on rails. It was a revolutionary idea, a heavy, steam-powered machine moving on metal rails to transport cargo. But early railways were extremely primitive. Rails were placed on simple wooden beams, and these beams were placed directly on the ground. The concept seemed practical at first, but when locomotives became heavier, problems quickly appeared. In 1825, George Stephenson opened the Stockton and Darlington Railway in England, the first public railway to transport passengers and freight. And in 1830, the Liverpool and Manchester Railway became the first fully operational modern railway line. These projects revealed a major engineering problem. The ground was not stable enough to support heavy trains. Early locomotives were heavy for their time, and their weight was concentrated on narrow iron rails. When trains moved over the tracks, the soil underneath would compress and deform. Rainwater made the situation worse. Wood rotted. Mud formed under the rails. Tracks shifted out of alignment. Derailments became a serious risk. Engineers realized something fundamental. Railways were not just about rails and locomotives. They needed a stable foundation system. During the mid-19th century, engineers began introducing sleepers, also known as railroad ties. Sleepers were placed perpendicular to the rails to distribute the weight of trains across a larger surface. This improved stability significantly. Engineers like George Stephenson and Charles Vignoles helped standardize track structures and rail support systems across Europe. But another problem remained. Sleepers were still resting directly on soil, and soil moves. It shifts with rain. It expands with temperature. It compresses under repeated pressure. Railways still needed a more stable base. By the early 20th century, another major problem began to affect railway systems. Wooden sleepers were wearing out too quickly. They rotted with moisture. They cracked under heavy loads. They were vulnerable to insects and temperature changes. Railway companies had to replace them frequently, which increased maintenance costs. Engineers started looking for a more durable solution. The first experiments with concrete sleepers began in Europe in the early 1900s, especially in France and Germany. But early versions were too rigid and often cracked under repeated train loads. The real breakthrough came in the 1940s and 1950s. French engineer Eugène Freycinet developed pre-stressed concrete technology, which allowed concrete sleepers to become stronger and more flexible under load. Railway companies like SNCF in France began adopting concrete sleepers on a large scale after World War II. Soon, Germany, the United Kingdom, and other European countries followed. Concrete sleepers offered several advantages. They lasted much longer than wood. They resisted moisture and temperature changes. They supported heavier trains and higher axle loads, and they required less maintenance over time. Most importantly, they worked perfectly with crushed stone ballast. The ballast continued to provide drainage, flexibility, and vibration absorption, while concrete sleepers provided strength and structural stability. This combination became the modern standard for railway construction around the world. By the late 1800s, railway engineers had already begun experimenting with crushed stone under the sleepers. Instead of placing sleepers directly on soil, they placed them on a thick layer of broken rocks. This system became known as ballast, and it changed railway engineering forever. The crushed stones created a stable and flexible foundation that could support heavy locomotives and long trains. By the end of the 19th century, ballast had become the standard in railway construction across Europe and North America. Railway ballast works because of three key engineering principles. First, load distribution. The stones spread the weight of trains across a larger area, reducing pressure on the ground. Second, drainage. Water flows between the stones instead of accumulating under the track. This prevents mud and soil weakening. Third, friction and stability. Crushed stones interlock with each other and keep sleepers in position. This creates a stable structure that resists movement and vibration. Engineers tested different materials over time. Sand moved too easily, soil compressed too much. Concrete cracked under vibration. Crushed stone offered the perfect balance, strong enough to support weight, flexible enough to absorb movement, and stable enough to hold the track in place. This is why ballast became the global standard. Trains generate constant vibration while moving. Steel wheels on steel rails create dynamic forces that travel through the track. Ballast absorbs and dissipates this energy. It acts like a natural shock absorber, protecting rails, sleepers, and locomotives. This extends the lifespan of railway infrastructure. Modern railway systems use advanced machines to maintain ballast. Tamping machines lift the rails, adjust sleepers, and redistribute stones automatically. This keeps the track perfectly aligned. Regular maintenance ensures safe and efficient train operations. In 1964, Japan introduced the Shinkansen, the world's first high-speed rail system. This marked a new era in railway engineering. Some high-speed lines began using slab track instead of ballast. Concrete slabs replaced stones to provide extreme stability at high speeds. Countries like Germany, Japan, and China adopted this system in specific high-speed corridors. However, slab track is extremely expensive. That is why traditional ballast is still widely used around the world. Even modern railways rely on crushed stones for flexibility and cost efficiency. If ballast were removed, sleepers would sit directly on soil. The track would begin to shift, water would accumulate, rails would lose alignment, and derailments would become more likely. In simple terms, railway systems would become unsafe and unreliable. What looks like a simple layer of stones is actually the result of more than 200 years of railway engineering evolution. From Richard Trevithick's first locomotive in 1804 to George Stephenson's railways in the 1820s and modern high-speed systems today, the ballast system became one of the most essential elements in railway infrastructure. It distributes weight, drains water, locks the track, absorbs vibration, and keeps trains running safely across continents. The next time you see a train passing by, look at the stones under the tracks, because without them, railways as we know them would not exist. If you want to understand how trains and railway engineering really work, subscribe to Rail Tech World. New videos every week explaining real engineering behind trains, locomotives, and railway systems. And if you enjoyed this video, leave a like and tell us in the comments, what railway topic should we explain next?